Thank you very much. Thank you. Indeed, I will speak about various continued fractions, at least at the end of my talk. So I would like to speak about approximation to one real number. So it means that we consider R2 here x, here y. Here is a straight line y equal alpha x, and we are looking for integer points close to this line. Okay. This is my joint work with Nikita Shulga from Australia. So he was my former student. Okay. Now, you can see that. If you will be interested in more details, we have a paper on archive. Okay? And I will start with the very beginning, with the basic of Diophantine approximation. So the first theorem which we should start when we have a lecture about Diophantine approximation is Dirichlet theorem. Dirichlet theorem means that if we consider a parallelogram close to, parallel to this line y equal alpha x, here t and here 1 over t, it contains, each such parallelogram contains an integer point. And in the title there was a notion of Dirichlet improbability. Here is the definition. So a number is called Dirichlet improvable if each smaller parallelogram with c over t with c less than 1 contains an integer. Okay, so I'm continuing with my next step. So Dirichlet, it is reasonable to formulate some results in terms of irrationality measure function. So irrationality measure function, I will draw it here. Here it will be t, here it will be value of irrationality measure function. And look, here we have an empty parallelogram with integer vertex. Then we shift its facet until it catches next integer point, and then make this parallelogram smaller and continue the process. So here will be q nu, q n plus 1, q n plus 2. And if we continue here, we have a graph of a slope of irrationality measure function, which is a piecewise constant function, q nu, q minus 1, q plus 1, q nu plus 2. That is irrationality measure function. Here is the definition. Dirichlet theorem turns into this inequality. Well, Dirichlet improbability means that this lim sup is less than 1, and a good tool is to study approximations is ordinary continued fraction algorithm. Well, and due to Lagrange theorem, continued fraction convergence are best approximations. I think that Lagrange theorem was mentioned in several lectures, in particular in the lecture of Slade Sanderson. Yeah? I will refer to his lecture several times, I think. Okay? But a little bit later. Well, so now I explained simple facts. Probably most of you know these facts, but nevertheless I decided to recall this. So this is decomposition alpha into continued fraction. Okay, this is convergent. Oh, I'm sorry, this is a typo. It is not alpha. I'm sorry, I missed somewhere. It is a typo. Not alpha. Okay, I will send my slides to the conference site, and I promise you that there will be no alpha. Well, so important things important objects are Lagrange constant and Dirichlet constant. I will explain in 1 second. Look, for our irrationality measure function, we have two types of points. The points which respect to beta approximations, and the points which respect which deal with uniform approximation. And so these points take care of ordinary approximations, and that points take care of uniform approximation. And these two constants, Lagrange constant, very well-known constant, which can be expressed in terms of continued fractions, deals with ordinary approximation, and Dirichlet constant deals with uniform approximation. We have nice Perron formulas in terms of continued fractions. Here I recalled that alpha n plus 1 is just the tail, and alpha star is inverse the beginning. And we have very nice formula which expresses this quantity, this product. By the way, this product is the area of this rectangle, while the product for Dirichlet constant is the area of the larger rectangle. Well, and I don't want to speak now about the values of this constant. This is another interesting story. I just will mention that Lagrange constant, the smaller value is 0, and the larger value is Hurwitz number. And for Dirichlet constant, the largest value is 1, and the smallest value is Sekerich number, which was first proven by Sekerich. Okay, so I recalled some basic facts. Now I'm continuing. Okay, I need to say a few words about Bedler approximability. What does it mean? Here is Dirichlet theorem. Dirichlet means that it is also always less than 1 over t, and sometimes it is the right order of irrationality measure function. So there are 4 equivalent definitions. The first one is just that irrationality measure function is bounded by below from constant over t. The second, which is equivalent, partial quotients are bounded. The third, Lagrange constant, is greater than 0. And the fourth is that Dirichlet constant is less than 1, strictly less than 1. By the way, the equivalence of the third and the fourth was, I am not sure that Davenport and Schmidt were the first who have documented that this is equivalent to that, but up to now I cannot find earlier reference. So Dirichlet improvability, it means, this is Dirichlet improvability, means that D is less than 1, it means that lambda is greater than 0, it means for irrational number. We do not speak today about rational numbers, because for rational numbers nothing is interesting, because from one moment this will be 0 and there is no mathematics. Okay, so this is a theorem by Davenport and Schmidt, and of course it is clear that we know a lot of about Bedler approximable numbers. They have 0, the set of Bedler approximable numbers has 0 measure, it has full Hausdorff dimension, it is winning in sense of Schmidt's game, and these theorems may be generalized to higher dimensions, but I will not speak now about higher dimensions. Well, I will continue with one, with approximation to one number. Okay, what's Bedler approximable numbers? Okay, of course, what is the next slide? It happened that quite recently people decided to do another job. Look, so what is Dirichlet improbability? We we are looking for integer points in parallelogram. What is parallelogram? We can consider a unit square, and we can make some linear transformation, linear map, to change this unit square into this parallelogram. And people, by some reason, I will explain what is this. This is a ball in L infinity norm with respect to subnorm. Instead of subnorm, you may consider arbitrary norm, and you may look for the corresponding process of approximating. What I am speaking about? I'm speaking about this process. Here we have a parallelogram with integer vertex. Yes? Then we keep these edges, but take this facet and move it until it catches next integer vertex. Then we rescale the parallelogram and continue the process, so we get convergence to continuous fraction. The same may be done for different norms, and this was first done by Duke and Anderson. Probably Duke and Anderson's paper was a motivation to study Dirichlet improbability by Kleinbock and Rao in terms of dynamical methods. And here are two papers, and a little bit less than 1 year ago, I participated in conference in Paris, where I had here a lecture by Kleinbock, and this was another motivation why I started to think about this problem. You may not believe that I was at this conference, or Kleinbock was in this conference, so I will show you. Look, here is a picture. There is Dmitry Kleinbock, and somewhere is me. So I hope, I hope some people here from the audience will find themselves as this. I see some do. Yes. Okay. So now, well, now I will give precise definitions. So first of all, instead of subnorm, we should consider what they call strongly symmetric norm. It is a mild restriction. Norm should be symmetric. There should be central symmetry. But we need some additional symmetry. Here we put absolute values and a technical condition that this point 1, 0 and this 0, 1 to just to it is easier. So we are dealing with unit ball. It is easier to consider dynamical point of view or point of view of parametric geometry of numbers. Here you see what I have done. I considered a straight line with coefficient alpha and approximated by integer points. It is better to fix a ball, not to consider this linear transformation. So it is better for dynamists, maybe not for me. But nevertheless, I am giving the formal definition. So we consider this lattice, this one parametric family of lattices, and we consider its minima, successive minima, with respect to the ball, which corresponds to our norm. Each such a ball has a critical determinant, and when we speak about critical determinant, there is a nice theory developed by Mahler. So, critical determinant, there are critical lattices, always exist critical lattices. The set of critical lattices may be considered in the space of lattices, and Dirichlet constant for the norm is defined similarly to Dirichlet constant for number in terms of something close to irrationality measure function, and number is called Dirichlet improvable with respect to norm. It means that this inequality holds. Here, this 1 over critical determinant just stands instead of this one. So if we replace norm by L infinity norm, it will be the same definition. Okay, well, what is the next? Few theorems which were announced in Kleinbock and Rau's paper. First of all, I will recall a theorem by Anderson and Duke. It is a dynamical theorem. It is an easy theorem because it says that if we consider a space of lattice, and if we consider a critical locus, the set of critical lattices, if we consider a small open set which contains this a neighborhood, then it is open, and because of ergodicity, almost all trajectory goes there infinitely many times, and this means that for almost all alpha we do not have Dirichlet improbability. This was formulated in Anderson and Duke's paper. However, Kleinbock and Rau observed something strange. This is an extended formulation. I do not read it now. There is something as irreducible norm. Irreducible norm comes from, this definition comes from Mahler. Norm is, roughly speaking, norm is irreducible if we can consider ball. This is irreducibility. What is irreducibility? If we consider ball, then if we consider a small, I am giving informal definition, a small segment of the boundary, then there exists a critical lattice which with point in this small segment. So if we deal with LP norms, this theorem, this restriction turned out to be very strong. It is clear that if we have P equal to ordinary Euclidean norm, then the condition is satisfied because there is a lot of symmetry. Any critical lattice may be rotated for any angle, and it will remain a critical lattice. Okay, so honestly speaking, Kleinbock theorem considered for LP norm deals with only one case, P equal to. In all other cases, we do not have irreducibility. But in P equal to, it gives an interesting result that if we deal with non-improvable numbers, so what was a statement of Schmidt's theorem, Davenport-Schmidt? So if we have Dirichlet improbability, then we have bad, and conversely, if we have bad, then we have Dirichlet improbability. Here, we do not have Dirichlet improbability, but we have bad, and it is possible for the set of full Hausdorff dimension. And one more theorem. So if it is zero measure, it is clear from previous result, but it has full Hausdorff dimension. In this paper and in his lecture, Kleinbock formulated several open problems related to description of these metric properties for different norms. And in particular, we can answer a lot of these problems. Well, so there are several theorems. There are several theorems which are corollaries of a general theorem. For instance, always Hausdorff dimension of Dirichlet improbability, but not B, is equal to 1. So Kleinvogt asked about Dirichlet improbability in different norms. So the most interesting norms you will see is L1 and L2. And we have set improbable in 1, but not in 2. So D with index is improbable in LE norm, because, L index norm, because I don't want to write here in the index LP, just P. So there is a lot of numbers which are 1 improbable, but not 2 improbable, and vice versa. Sometimes the set of Dirichlet non-improbable numbers does not contain badly approximable numbers by some reason. There are two magic numbers, P0. It is Davis constant. I will explain what it is later. And sigma P. Sigma P is a solution of such equation. It is an easy constant. And existence of badly approximable numbers, which are not Dirichlet improbable for this interval, is related to the property of just one number, of just badly approximability, of just behavior of continued fraction for the root of this equation. Well, I'm continuing, so I'm sorry. This is a complete structural theorem. Which shows criterion for badly approximability for every P. So it is too complicated. So what was before are corollaries. I think that it is not possible to understand, at least during the lecture, but maybe even during looking at the paper. So I decided to look into with microscope here. So if you look with microscope, you will see this. Please do not be afraid. This is D1. This is D1. You should not look here. You should look just for at this line, because this theorem states that Dirichlet non-improbability can be expressed in terms of continued fraction to alpha. And this, in fact, this is related to Minkowski diagonal continued fraction. I will tell it a little bit maybe in the last minutes. Well, to have non-Dirichlet improvable number, you need to have in continued fraction expansion for alpha something like palindrome. So here you should take something this. Then 2 ones, and it is not just exact palindrome, because here, due to something like folding lambda, you need to write B1 plus 1, but it is palindromic, and these are variations on this line. So, in some sense, Dirichlet non-improbability for L1 is equivalent to existence of palindromic patterns in continued fraction expansion. In L2, the situation is a little bit more funny. So here I do not write cases, as on previous slide. I just wrote one condition. So there are two numbers which are related by this equation, and the pattern which take care of which is response on Dirichlet non-improbability is organized as follows: in one direction one number, in another direction another number. So now the secret why it happens so. There is a long story about describing critical lattices for this domain, for the box. It started with Minkowski. It started with Minkowski with false conjecture. Davis realized that this conjecture is false and improved the Minkowski conjecture. There was a long story with many results because it turns out, although theoretically the problem is almost trivial because any critical lattice has three points, z, y, and z plus y on the boundary, and there is nothing to calculate theoretically, but practically there are difficult calculations, and from some times passed, and at last by Malyshev, he was a student of Linnik, with his students produced a numerical proof of Minkowski conjecture, and a complete description of all critical lattices for all p, to be honest, we did not check this paper because it is related on computer calculation, but in literature, people do believe that this result is true. However, some time ago, we were able to find some mistakes in Malyshev's papers, but not related to this problem. So I believe that this is true, but they do it with computers in '86. I think that now it is much easier to do it with computers, and I think that continued fractions, better formulas for continued fractions, clever formulas for continued fraction, may enable somebody to give a proof without computer. So, but this is not done yet. Okay, so I will continue quickly with a description of critical lattices. So, what are critical lattices? There are two types of critical lattices. One have point on the coordinate axis, and then this segment between z prime and z2 prime should be parallel to this. This is one type of critical axis for p less than p0. Now for p greater than p0, there is another type of critical axis. We have bisector, and we have 2 points parallel to bisector. What is p0 Davis constant? So in the first case, in the first case, we have lambda 1, and we have that determinant of this lattice. In the second case, we have determinant of lattice 2, the second case. And when they are equal, this is a special value of p. This is p0 Davis constant, for which they write that is 2, 5, 2, and something else. The equation is complicated. So for L1 norm, we have a square, and I draw here two different critical lattices. This critical lattices is very specific because here this point and that point have the same coordinate, and typical critical lattice has different coordinates. Okay, I do not speak about, I do not have a picture for L2 because everybody understands Euclidean norm. However, here is a description of critical lattice, and I will say a few words about this equation. You may remember that there was equation beta beta star equals 3. So you should parameterize these points on unit circle by not a very, not the most trivial way, and then you should manipulate with this parameter. I didn't write 5 formulas because it is not possible to understand. But then you get an equation of such a type. Well, what is most interesting? I would like to finish in 1 minute with the most interesting case, with the case of L1 norm. You may remember that I said that the criterion is some kind of palindromicity. In L1 norm, what happens in L1 norm? So instead of doing this, you should take an integer point, you should take this triangle, and you should rotate this triangle until you catch another integer point. This is Minkowski algorithm. As was said in last lectures, these points, these extremal points, will be convergence, but not all convergence. Minkowski proved a beautiful theorem that convergence for this fraction are just those convergence for which Legendre inequality holds. And if we deal with irrationality measure, corresponding irrationality measure function, you see, here are these points. You can take a convex hull of these points. This will be a piecewise linear function. Some of the points will be omitted. And this is a formula. And if you consider a specter for this function, so the values of this lim sup, then it can be easily calculated. You should write in an explicit manner the singularization area. It will be here with some hyperbola. So, and you should deduce a little bit complicated formula for this in terms of volumes somewhere here. And it is easy to prove that this value attains to minimal value 1/4 and maximal value 1/2. The problem that is very mysterious, for L1 norm, I cannot say anything reasonable about other values of this lim. So the study of Lagrange spectrum or Dirichlet spectrum is very extended, but here for this spectrum, I know minimal value, I know maximum value. Of course, I can calculate it for any quadratic rationality, this value, but I even do not know if there is any number which doesn't belong to this spectrum. I do not know if golden section is isolated. So thank you very much. I think I should stop here. Okay.